Swayam Prabha. Digital India. Educated India.
So we had started on three-phase AC voltage controller with R load at a firing angle of 60 degrees. So we'll look at it for a firing angle of 30 degrees, which will probably tell you how you are really having variations in the voltage waveform. So let me try to take it for alpha equal to 30 degree for R load. So I am trying to look at R load with alpha equal to 30 degrees, right? Then we will proceed to RL, and with that we will conclude AC voltage controller. We are not going to dwell on it for too long. So we said that we are going to have three-phase voltages, and I am going to have one, this is A phase, so 1 and 4, then I am going to have B phase, which we call 3 and 6, and then C phase, which is going to be 5 and 2. And then we are connecting the load here. I have taken star connected source and star connected load, and AC voltage controller is just connected in between, right? So if we are looking at this with alpha equal to 30 degrees. So these are the three-phase voltages that I need to draw. So this is one of the phase voltages. So I am going to have this as the 60 degree gap, and then let me draw the second phase, which is going along somewhat like this, right? And the third phase, which will go along somewhat like this. So this is A, this is B, and this is C, and we are firing at 30 degrees, which means we are going to fire one here, then, oh, I'm sorry, one here. I am drawing it as though it is rectifier. So one has to be fired here, and two has to be fired here. So this has to be erased. Oh, the entire waveform is erased. Okay. So this is somewhat like this. So 2 is fired here, then 3 is fired here, and so on. You guys understand that this is alpha equal to 0 for AC voltage controller, right? So because of which I have 1, 2, 3 and so on like this. So when I fire 1, I assume 5 and 6 are conducting. So if 5 and 6 are conducting, 5 corresponds to C phase, but C phase negative happens only from this point, not before that. So I am going to have C phase negative only from this point. So I still have 30 degree interval before device number 5 goes off. So I am going to have, so let me draw the intervals. So this is again omega t. So here 1 is fired, and here I am going to have actually 5 going off. 5 will go off only where I have shown like this. So here 5 goes off, right? So that means for 30 degrees I am going to have 5, 6, 1 conducting. So for this duration I will have 5, 6 and 1 conducting, even for R load. I am talking about R load. If 5, 6 and 1 are conducting, all the 3 phases are connected to the load. So if I am trying to look at the voltage across ZA, So this is VZA. So VZA is going to be VAN itself. So whatever is VAN, so something like this, is going to be the voltage waveform. This is VAN. If you look at this portion between these two, that is where 1 is fired and it is 5 is going off, that is exactly this portion of VAN. So I'm going to have VAN coming up during this portion. But after that I'm going to have 6 and 1 conducting until 2 is fired. So 2 is fired only at this point. So until 2 is fired I will have 6 and 1 conducting. If 6 and 1 are conducting, 6 belongs to B phase and 1 belongs to A phase. So it will be VAB by 2. Please note, if I try to look at VAB, VAB is going to be actually 30 degrees ahead of VA. So it would have almost reached peak even earlier. So it would have been coming down slightly. So I have to look at what is the difference, but this is going to be VAB by 2. I will have VAB by 2 because I'm going to have VAB coming up across these two loads simultaneously, that is ZA and ZB respectively. So I have to look at what is the voltage across ZA. So load per phase voltage. We are looking at per phase voltage of the load. So it will be VAB by 2. Then again when I fire 2, I'm going to have until this point where I'm going to have the voltage of B goes into positive direction. 6 will continue to conduct. 6 will not go off. So I will have 6, 1, 2 conducting here. 6, 1 and 2 conducting here. If 6, 1 and 2 are conducting here, anywhere 3 devices conduct, I will have per phase voltages coming up directly. So I will have the per phase voltage which is again VAN. So I may have a jump in the voltage, something like this, and then this is coming down. So this is again VAN during this portion. So I will have VAN, VAB by 2, again VAN, then 6 will go off. So 1 and 2 will come, 1 and 2 will correspond to VAC. So VAC by 2 will come. So I am going to have line voltage, half of line voltage and phase voltage coming up alternately. But will there be any zero voltage at all? That we have to check. So if I say that 1 and 2 are conducting here, maybe I am going to have, this is VAC by 2, maybe. I don't know the magnitudes. I have to analyze it clearly. Unless I really analyze the magnitudes, it's difficult. After this, 1 and 2 have conducted. Now 1, 2, 3 will conduct. I hope you understand. When I fire 3, still for 30 degrees, I will have 1, 2 and 3. So 3 is fired here. 3 is fired at this point. So I am going to have in all probability 1, 2, 3 conducting. Right? Is 3 fired there? Have I made a mistake? Here. So have I made a mistake in writing the firing angles? This is 1, this is 2, this is 3. Sorry. This is where 3 is. This is where 3 is. So this has to be erased again. Right? So this is where 3 will be fired. 3 is fired here. So when 3 is fired, still there is some amount of positive A phase voltage left over. So 1, 2, 3 will conduct together. Right? So I am going to have actually for the first 30 degrees starting from alpha, I am going to have 5, 6, 1. Then for the next 30 degrees, I am going to have 6 and 1. Then for the subsequent 30 degrees, I'm going to have 6, 1, 2. Then I will have 1, 2. Then I will have 1, 2, 3. Then I will have 2, 3. This is the sequence that it is going to go on, right? When 2 and 3 are conducting, there is no A phase voltage. A phase will not carry any current. A phase load will not carry any current. So here there is no current through A phase. No current through A phase. So I'm going to have essentially whatever is the VZA will be 0 during this 30-degree interval. After that we will fire 3, 4. Once we fire 4, again we will get negative side voltage, because it will essentially allow the current to flow in the opposite direction. Is this clear? We are looking at each of the conduction of the device, like what is the combination of devices that conduct for one interval. And I have taken a specific case, alpha equal to 30. When I take alpha equal to 30 with R load, this is the way it is. If it is RL load, it's more complication. I hope you understand, because if it is RL load, the inductance will forward bias the device even after the voltage goes negative. If the voltage goes negative, still I am going to have the device to be forward biased. So if the device is forward biased, I am essentially going to see that even after, for example, here we said phi will stop conducting once I have the C phase voltage start going negative. But phi will continue to conduct even after the C phase voltage goes negative. Right? So which means the 3-device conduction can extend for longer and longer, depending upon how much is my inductance voltage. But if that continues until the next device is also fired, then always 3 devices will conduct. That's when you won't have any control. All the time per phase voltage is going to come up. So in which case you will hardly see any control over the output voltage. So you would see more control over the output voltage, especially in the case of RL load only if alpha is somewhat larger. Otherwise you are not going to see much of control over the output voltage at all. So much so for AC voltage controller. So in AC voltage controller we had seen only single phase and 3-phase star connected case, R load, RL load, and for single phase I said why alpha greater than phi only will give you control, where phi is the load power factor angle. We have not looked at any rigorous mathematical expressions. I just want you to understand how it works. That's it. Okay. Now the next one that we are going to take up for AC to AC converter. The second type of AC to AC converter is cycloconverter. Cycloconverters are again generally made up of SCRs, thyristors. That's the reason I'm taking up all those circuits which are involved with thyristors. I'm taking up all those circuits, and that is the reason why I wanted to just take up this also along with line commutated circuit. What I mean by line commutated is supply voltage is trying to make sure that the device that goes off is reverse biased for sufficient amount of time. You don't have to apply any external voltage. The supply voltage itself is taking care of the current transfer from one particular device to another device. So cycloconverter also falls under that category. So because of which this one heavily depends upon the supply voltage being AC. The output voltage is not going to aid in commutation. More than that, the supply voltage is going to aid in commutation. That is the way it is going to work. So this converts AC to AC directly, and if I have 50 Hertz, for example, I may be able to convert it only to a lower frequency. hardly ever we will use it for a higher frequency conversion. So cycloconverter will convert both magnitude as well as frequency, but the frequency will be decreased or stepped down in frequency as far as input-output relationship is concerned. So normally input frequency will be higher than the output frequency. That is the way normally the cycloconverter works. So if I am trying to look at the basic principle of a cycloconverter, we'll look at the circuit a little later. If I am going to have, let us say, an AC supply single phase somewhat like this. I am going to have the single phase AC supply like this. If I use a rectifier for rectifying one cycle, so I am going to rectify this as well, and I am going to rectify this such that I am going to get basically this as the output across the load for 2 half cycles. I am talking about 2 half cycles. For rest of the 2 half cycles, I am going to have another rectifier which is connected exactly like a dual converter in the opposite sets. Then I will have this portion and this portion coming up as the output voltage across the load. So I have got 2 halves of positive half cycle, 2 halves of negative half cycle. This is going to repeat itself. Let us say I am going to again have 2 halves of positive half cycle, and then I am going to have 2 halves of negative half cycles. Now what will be the frequency? Forget about the waveform. Waveform is not sinusoidal. Very clear. There is no doubt. But what about the frequency? The frequency is going to be 50 by 2. Right? If this is 50 hertz, I am going to get 50 divided by 2. I am going to get 25 hertz. Right? I cannot do this with diodes. I hope you understand, because diodes will conduct no matter what if they are forward biased. So I can't even have a dual converter with diodes. I hope you understand. I can't connect back to back. It is going to essentially burn completely, because one will have plus on the top and minus at the bottom. The other one will have minus at the, again the other way around. So you will try to connect the two plus and minus. Imagine the dual converter. I am talking about a dual converter. So I am going to have something like this, single phase. So I am normally going to have it with thyristor. It cannot be made with diode, right? And I am going to have a load here, right? And this is my input supply voltage, right? On the other side, I am going to have again another fully controlled converter, somewhat like this. So if I am having diodes, I will not be able to delay the conduction at all. So for this, if this is plus and minus, for this, actually this will be plus and this will be minus if it is diode. So I am trying to connect the plus and minus together, right, directly, and that is definitely not done. Huge current will flow. So you cannot do this. That is the reason why in the dual converter we wanted to have this was plus and this was minus. We made this alpha greater than 90, whereas this alpha less than 90. If you may recall, this is what we did in the dual converter, right? And after all, we had the input from the same AC voltage. So I would say maybe this went here and this went here. This is how they were connected. You remember, this is the way the AC supply voltage was connected. So here is my AC supply. Cycloconverter is no different from the dual converter as far as the circuit diagram is concerned. Only difference is, in dual converter, we were operating one at alpha less than 90, the other one at alpha greater than 90, and we were making sure that alpha 1 plus alpha 2 equal to 180. This was the control that we wanted to have, if you may recall. So that the average voltage across this and the average voltage across this, averages are the same, not the instantaneous values. They were different, right? So the averages were the same, because of which we actually had put a reactance here. If you may recall, we had put some reactance here. So that if there is any di by dt, that will be limited, and the reactance will also have some amount of resistance, because of which the current will be limited. Magnitude of the current will also be limited. But in this case, in cycloconverter case, if I may call this as the negative side converter, which is N converter. I may call this as positive side converter or P converter. I will make P converter work for a distinct number of half cycles. I will make the N converter work for a distinct number of half cycles. Both of them will not work simultaneously. They will not work simultaneously. And each of them functions as a rectifier in its own right. When P converter is functioning, it is working as a rectifier on its own. And N converter is quiet. It is not working because you will not give any pulses to the N converter. So N converter pulses will not be released until P converter current comes down to 0. Then you will release the pulses to N converter, holding off the pulses to the P converter. So what is going to happen is, for the first two half cycles, for example, I will have the current flowing like this. Right? So this is during P converter operation. So this is first two half cycles. The next two half cycles, I will have a current flowing like this. This is for next two half cycles. Right? So I am going to have, for the first two half cycles, the current is going with plus here and minus here. For the next two half cycles, the current is going with plus here and minus here. Right? So which means in both the cases, I will have alpha less than 90 only. Both alpha 1 and alpha 2. So this is for cycloconverter operation. Both alphas will be less than 90, but they will work completely disjointly. They will not work together. When one is working, the other one will not be working, and vice versa. Whereas, when I am talking about dual converter, these two work together. One works as a rectifier, the other one works as an inverter, and they work together such that I am going to have the DC link voltage average value to be the same. So here this is for dual converter. Right? So what I can do is to have basically multiple number of half cycles being worked with P converter. Make sure that the current goes down to 0. So if I have RL load, I have to continuously sense the current. If I don't sense the current, I can get into trouble, because I will still have maybe some positive negative left over, and if I try to fire this, there will be a dead short, because this would not have gone off, and this will start conducting. So I can have really a dead short circuit between the two converters, P converter and N converter. So I have to make sure that the current really goes down to 0 in the P converter and the load. And after that I should start the other half cycle of the output. So we are looking at two input as well as output, both are AC. So I have to talk about whether it is a positive half cycle of the input, positive half cycle of the output, negative half cycle of the input, or negative half cycle of the output. So if I want positive half cycle of the output, I have to make use of P converter. If I want the negative half cycle of the output, I have to make use of the N converter. So distinctly I have two converters which are connected back to back, which are going to work in such a way that one is disjoint with the other. They are mutually exclusive. They are not going to work together. But I have to make sure that the current comes down to 0 before I release the pulses for the next set of devices. right? And when I release the pulses to the devices, just like what we did, 1 and 4 will be given pulses during positive half cycle of the input. And 2 and 3 will be given pulses during the negative half cycle of the input. And I may call this as P1 because P converter, P2, P3 and P4. So P1 and P4 will be given pulses during the positive half cycle of the input, provided I want positive half cycle in the output as well. Right? Whereas, if I want the other way round, if I want the negative half cycle at the output, then I have to take care of these devices. So, if I may call this as, this is coming to A. So, if I say that this is coming to this one, so I should call this as N1. So, this will be N4 and this will be N2, this will be N3. So, I should correspondingly make sure that N1, N4 will be given pulses if I want negative half cycle in the output, but prevailing thing is the positive half cycle as far as the input is concerned. So, I have to look at the input as well as output simultaneously. So, this is going to be the way your complete converter works. So, this is single phase to single phase operation. I can have the same thing for single phase to three phase to three phase to single phase. So I can have multiple types of cycloconverter connections. So when I am talking about the single phase to single phase, that to full wave, because I'm not leaving out the other half. I'm always using both the halves of the input wave, whether it is positive half or negative half. I'm making sure that I'm making use of both of them. So it is a full wave controlled converter. What I have used is a full wave, fully controlled converter. So when I use a fully controlled converter, even single phase to single phase conversion will require 4 plus 4, at least 8 devices. You get my point? So if I want single phase to single phase full wave cycloconverter, I will require 4 plus 4, 8 devices minimum. I will require at least 8 devices. Only then I will be able to do full wave to full wave. If I want now 1/3 of the frequency, I can make 3 half cycles positive, 3 half cycles negative. So you guys know how to reduce the frequency further. But we will not be able to increase the frequency with single phase, because the thyristors will go off only when it is starting to go into the negative half cycle. So I cannot increase the frequency unless I use some kind of forced commutation. But the moment you use forced commutation, the entire thing will become very, very complex. So generally, we do not use SCR based cycloconverter for increasing the frequency, because if you want to increase the frequency, you necessarily need to put forced commutation circuits. You have to turn off the devices somewhere in between. Let us try to take a look at a 3-phase